Intermolecular forces, what are these? Well, inter, so between, molecular, between molecules. So these are forces that exist between molecules, okay? All right, so you can think of intermolecular forces as molecular tethers. So basically, we have these interactions that our molecules have that keep them tethered together. You can think of, say, towing a camping trailer, all right? So if I want to go camping, I hitch my trailer up to the back of my car. I have something really strong that holds the trailer to the back of my car so that as I'm driving, it doesn't separate. There are different things I can use to do this towing. If I were to say, I don't know, grab a piece of yarn and try to hitch my trailer up to my car with that, it's not going to work so well. It's going to break really easily. But if I use really strong, really reinforced steel cables or strong, rigid pieces of metal, that's going to hold my trailer to my car much stronger. So we have different intermolecular forces that are going to tether molecules together with varying differences in their strengths. So we have a couple of different things going on. We have these van der Waals forces, where we call those our London or dispersion forces. Dispersion forces are the better word, but they still get called London forces all the time. Then we have polar-polar interactions. So those require having a dipole moment. So they're also called dipole-dipole interactions. And then a special type of dipole-dipole interaction is a hydrogen bond. It's not an actual full-on bond, but it's an interaction between hydrogen and one of three different other atoms. So just to recap, remember with polarity, okay, not only do we have to have polar bonds, but we also have to have a shape of our molecule such that we have a net direction of molecular polarity. So again, with carbon dioxide, it's linear, so if I have oxygen pulling me here and oxygen pulling me here, they're going to cancel each other out. And while the carbon-oxygen bond is polar, the molecule itself isn't, because the symmetry causes it to cancel out. Water, though, we've got polarity going this way, and so they converge on each other, and we have a net direction of polarity that goes up the middle there. Okay, and so you can see here we've got various different polar molecules on the top, and on the bottom we've got a couple non-polar. So that tetrachloromethane, that's not polar, because even though the carbon-chlorine bond is polar, I have 4 perfectly symmetrical chlorines around that carbon, so they all cancel each other out. Okay? All right, let's look at our London forces, or our dispersion forces. Everything has dispersion forces, okay? Everything has dispersion. So even if something has a dipole-dipole force or a hydrogen bond, it's still also going to have dispersion forces. Everything has dispersion forces. So what happens is our electrons are all moving around. If something comes along and causes the electrons to kind of shift all to one side, well, now I have a little bit of a concentration of negative charge on one side, and I've got a dearth of negative on the other side, so I've got the positive charge from the nucleus being felt there. And so I get this polarization where now all that negative charge here and that open positive charge here causes the molecule or atom next to it to shift their electrons around, and so we get these instantaneous polarizations that we end up getting stuff to shift all their electron clouds and interact with each other. Okay, so our nonpolar substances, this is how we get them to condense. When I look at these, okay, the strength is going to increase with the number of electrons. This makes sense, because where am I going to have a stronger concentration of negative charge? When I have 1 electron, or when I have 10 electrons, or when I have 30 electrons? All right, so more electrons means we're going to have stronger dispersion forces. The shape of the molecule also matters. So if you look here, I've got 2 things with the exact same formula. Okay, we have 5 carbons and 12 hydrogens for both of these. Okay, so these are both C5H12. Okay, so same number of electrons, same molar mass. The difference is the shape. If I have something that's balled up, I only have a few points of connection. But if I have something that's flatter, I have lots more points of connection. And so I have more places for my molecules to interact with each other, so the forces get stronger. We can see this with the boiling points. The balled up neopentane has a boiling point of only 9.5 degrees Celsius, whereas the straight chain N-pentane has a boiling point of 36.1 degrees Celsius. So significantly higher than the neopentane. So it takes more energy to disrupt and break those tethers. So when I boil something, I'm going from a liquid to a gas. All right. And so basically, my liquid, I've got all those tethers holding things together. And to go from a liquid to a gas, I have to break those tethers. And so the stronger the tether, the more energy to break it. And so it takes more energy to break the tethers in the N-pentane because I have more places for things to interact. Okay? All right, then we have our dipole-dipole forces. So our molecules that are polar have a permanent positive, partially positive end and a permanent partially negative end. And so what do we know about positives and negatives? They attract each other. And so I get these attractions because of the permanent partial positive and permanent partial negative ends on my various different polar molecules. Right? So these are typically a little stronger than our dispersion forces. I say typically because if I'm comparing two things of similar size, the dipole-dipole forces will be stronger. But if I'm comparing a really big molecule that only has dispersion forces, like a really long hydrocarbon, all right, to something small like, I don't know, methanol, that really long hydrocarbon and methanol aren't good comparisons because the really long hydrocarbon is going to have a lot of points of connection for those dispersion forces. So when we compare things of similar size, the dipole-dipole forces will win out. Okay? All right, so I have a couple pictures here. I have one picture that shows two molecules that don't have any polar clouds there. So these guys are non-polar. So the only forces these guys have are the dispersion forces. Okay? Now, my second picture shows a sample of something that is polar. Okay? So, our polar substances still have dispersion forces. Because everything has dispersion. But they also have dipole-dipole. Okay? All right. Okay, and then our last force is our hydrogen bond. So this is a special type of dipole-dipole force. So for a hydrogen bond to be present, we have to have a hydrogen bonded to something that is small and really electronegative. So nitrogen, oxygen, and fluorine fit this bill. Nitrogen, oxygen, and fluorine are all very electron greedy. Fluorine is the most electronegative element on the periodic table, followed fairly closely by oxygen. So in these bonds, what ends up happening is the electron density is attracted more strongly to the fluorine, to the oxygen, to the nitrogen. And so we have a really strong partial negative on these guys, whereas we have then a fairly significant partial positive on the hydrogen. And what happens? Well, those hydrogens, they're electron poor. They want more electron density. And so if there's another nitrogen, oxygen, or fluorine that's flush with electrons floating around, they're going to go, hey, I want to hang out with you, and they're going to form a fairly strong attraction. Not a full-on bond, but a fairly strong interaction between the hydrogen and the nitrogen, the oxygen, or the fluorine. Now, it's really important. For a hydrogen to participate in hydrogen bonding, it must be bonded to a nitrogen, an oxygen, or a fluorine. But for nitrogen, oxygen, or fluorine to participate in a hydrogen bond, they don't have to have a hydrogen on them already. They just have to be a nitrogen, an oxygen, or a fluorine, okay? So here's a couple pictures, okay? Some textbooks and places end up drawing hydrogen bonds with dots. I studied hydrogen bonding very, very extensively for many years, and everybody I know always used dashes for hydrogen bonds because the dots look too much like electrons when you're not using different colors. So I would draw, like if I had another water molecule here, I'd have my lone pairs, and then I draw my hydrogen bond with dashed lines like this. Okay? All right, so we get these hydrogen bonds between those incredibly partially negative oxygens or nitrogens or fluorines, and then those poor hydrogens that electron density just does not spend much time with them. Okay, and so you can see water, we get all these hydrogen bonds. And water is really interesting because water can actually form 4 simultaneous hydrogen bonds. Now, hydrogen bonds are not just present in water, all right? They're present in a lot of other things too. So you may have learned with DNA, we have the base pairing of adenine to thymine and guanine to cytosine. Well, why do we get that? We actually get it because of hydrogen bonding. So here's a picture of our DNA. Okay, so here's our ATGC pairing. Well, what we're getting between adenine and thymine are 2 linear hydrogen bonds. So very head-on, very straight, very strong. And between cytosine and guanine, we have 3 simultaneous hydrogen bonds. Okay? Now, do we get a hydrogen bond between this oxygen and this hydrogen? We do not, because this hydrogen is attached to a carbon, and you have to be on an oxygen, a nitrogen, or a fluorine to participate in hydrogen bonding, okay? But an oxygen, nitrogen, or fluorine can take a hydrogen bond, which is why this nitrogen right here doesn't have any hydrogens but can take a hydrogen bond. This oxygen right here doesn't have any hydrogens, but it can take a hydrogen bond. Okay? If I tried to pair, say, thymine up with guanine, okay? Well, this and this would pair up. So this one right here and this one right here would pair up. Okay, we could get a hydrogen bond there because I've got that NH2. But here and here, we would not get a hydrogen bond because if I have a hydrogen sticking out and a hydrogen sticking out, the hydrogens are not going to hydrogen bond with each other. Okay, and then I would have an oxygen and an oxygen paired up, and that's not going to give me a hydrogen bond. So I might be able to get one fairly weak hydrogen bond between thymine and guanine, but I'm not going to get these multiple linear, straight head-on, amazing hydrogen bonds that hold that together. Okay, and so we get all these hydrogen bonds that give us our DNA. Okay, we also get hydrogen bonding in proteins. So proteins, in order for them to fold, must be able to have their interactions with the different parts. So if amino acids miscode, the right things aren't going to line up, and so we're not going to be able to get the linkages that we need, and so we're not going to get the protein folded correctly, so it's not going to work correctly. And so one of these things involved in protein folding is hydrogen bonds. There's other things, as you can see here, but one of the important ones is hydrogen bonding. Okay? When we do things like cook, we denature things, and so they have their linkages. We cook, we break those apart. Okay? All right, so now let's take a look at a couple things here. Okay? Let's figure out which ones can hydrogen bond. So this one only has carbon and hydrogen. Do I have oxygen, nitrogen, and fluorine? No. So this one is no hydrogen bonding. All right, now I have methanol, where I have a CH3 group bonded to an OH. So it'll look like this. So can I get hydrogen bonding there? Yes, I can. Okay? And then here, this part right here would be this. So can I get hydrogen bonding? Yes, I can. All right, so let's take a look at what that would look like. All right, so for my methanol, oh, okay, that was really weird. Okay, I'm just gonna try to draw it over here. My iPad has been a little touchy lately. So I have my iPad connected to my computer so that I can write on everything. All right, and then we can get a hydrogen bond like that. Okay. All right, and then okay. When I look at my other molecule, I'll put it down here. Oh, whoops. I'm gonna run out of room. There we go. I'll kind of draw it like that. So I can actually get a situation where I get two simultaneous hydrogen bonds here too. Okay. So I can get a hydrogen bond here and a hydrogen bond there. I could also get a hydrogen bond between one of those hydrogens that's on the nitrogen and one of the nitrogens as well. Okay, so we get hydrogen bonding that looks like that. Now, when we look at these, okay, the previous slide that this jumped over was just showing how strong bonding forces are. All right, now for our intermolecular forces, we talked about hydrogen bonding, dipole-dipole, and our dispersion forces. So you can see on here, okay, the strength of these, all right? So overall, hydrogen bonds are the strongest of these forces. But if you look down there at our dispersion forces, they can actually be fairly strong. Again, if you have a really, really long molecule where there's lots of points for things to connect and interact with each other, you're going to wind up having a fairly strong set of intermolecular forces. So when we compare them to each other, we have to compare things of similar size. Because when I start comparing things of vastly different size, then things start to get a little bit harder to compare from molecule to molecule. But molecules of similar size, yes, our hydrogen bonds are going to be our stronger forces. But as we get bigger and bigger, we can actually get really strong dispersion forces. So if you remember, viscosity, okay, is one of the properties that liquids have, that resistance to flow. If I have a really, really, really long hydrocarbon, like a long oil, that's not going to flow very easily. I don't know if you've ever tried to pour really thick oils like into your car or for something else. They can take a while to pour because they're sticking to each other, and so they don't flow very easily. So those dispersion forces can get really strong. Okay? So those are our intermolecular forces.